Okay, this is a bonus lecture, a lecture just to review for the upcoming exam. So exam 3, which will be on Tuesday, April, 8th, I think, will only be covering 3 chapters. Chapter 25 covering geometric optics, Chapter 26 covering vision and optical instruments, and Chapter 27 covering wave optics. So Chapter 25 was really a full chapter. Chapter 25 we spent a lot of time on. We learned that light can be treated as a ray, that is, it travels in a straight path. And because of that, we can use geometry to figure out how images are formed. Huygens principle, which says that if we have light traveling, we can take any point along a wavefront. So make sure you know what a wavefront is. Any point along a wavefront, and it can be treated as a new point source for light. And then you take how those new point sources superpose, how they add up to calculate how the light propagates or travels. So make sure you understand Huygens principle and can apply it. Then we have the laws of reflection and refraction. Remember, light goes different speeds in different materials. So we had the index of refraction, N, which was defined as the speed of light in vacuum, C, divided by the speed of light in whatever the material is. And refraction, the bending, followed Snell's law. When you go from one material to another, N1 times sine theta 1 equals N2 times sine theta 2. Now, light works the same forward and backward, so it doesn't matter which medium is 1 and which one is 2. It's just you have to have those mediums. And it's very important that these angles, theta 1 and theta 2, are measured from the normal to the surface. They're not measured from the surface to the incident ray or from the surface to the refracted ray. They're measured from the surface normal to the incident ray and surface normal to the refracted ray. The law of reflections was much simpler. The law of reflections was that theta incident equaled theta reflected. And so based on those two, we were able to make things that focus light. So focusing light, if you use a mirror, if you have parallel incident rays coming into that mirror, those parallel rays will bend like that and come to a point that we call a focus there. Now, we draw things as spherically shaped mirrors. In truth, for parallel rays, you actually would need a parabolic shape. So the spherical shape we use isn't perfect, but that's how we define the focal point. So what if I have a mirror that is convex instead of concave? Then if I have incident parallel light, that second one wasn't very good, it will reflect away. And so it doesn't come to a focus, right? But if you extrapolate those rays, the extrapolations meet. And so where those extrapolations meet, we call that a focal point as well. But this is a virtual focal point. Virtual because they didn't actually meet there. And using our sign conventions, this is the focal distance. F is negative for the virtual focal point, whereas over here, this was a real focal point, and F is positive. So positive with focal length as well as image distances occurs if you have the rays actually meeting there. Negative is when it's virtual, when the rays don't meet there, but the projections of the rays meet there. Coming back to total internal reflection, because I kind of got ahead of myself. Total internal reflection is what occurs if you have light going from, let's say, N1 is equal to 1.5, so that would be like a glass, into N2 equals 1.0 into air. In that case, the light should bend away from the normal because it's going to a faster medium. And if you have it at what we call the critical angle, so here, let's draw the surface normal here. If you're at the critical angle, then the light will refract parallel to the surface using Snell's law. And if you have any angle bigger than that critical angle, you have what turns out to be sine theta is greater than 1, which isn't possible. And in that case, Snell's law no longer works, and instead the light is totally internally reflected. So if I had instant light at any angle bigger than that critical angle, then the light would just reflect and follow the law of reflections. You have a rainbow is an important thing. Light or water is a dispersive medium, which means the index refraction actually is different for different colors. And so when you have the light from the sun, which I will draw here as yellow, even though we know it's not really yellow, it's more whitish, and it hits a droplet of water, that light separates, so different colors bend different amounts. And then they come out like this. And so if you look at the rainbow, you see different colors at different angles because the geometry for these angles is very strongly set. That's a first order rainbow. A second order rainbow occurs when you have two reflections internal instead of one. And notice that with this one reflection, there was a crossover between the red and the blue and the violet. If you had two reflections, you'd have two crossovers, and so the colors reverse. Then the last part, and this is really big, be able to find image positions and heights produced by either a lens or a mirror, and you should be able to do it either graphically or calculationally. So I have a couple slides here to go over how to do this. So if you're doing a graphical ray construction, and for the exam, even though it's going to be an oral exam done with Zoom, I'm going to have you pull out a piece of paper and a ruler and draw, and I want to see how you're doing it as you're doing it, a ray diagram. And so I will give you, and everyone will have a different variation. I'll decide beforehand what it's going to be, but it'll be different for each of you. Well, there's 10 of you, and there's not 10 total options, but you will have either a lens or a mirror. So you'll have lens or mirror, and then it'll be either a converging, that has a positive focal length, or a diverging. That's 4 options. And then you'll have the object closer or farther than the focal point. So that gives us a total of 8 variations there. So there'll be a couple that have the same thing, but generally speaking, you'll have something different for each one of you. And so you're going to need to draw the principal axis and then draw your lens or mirror, and make sure when you draw it, you identify the primary and secondary focal points using an accurate scale. So you do want to have a ruler available with you. Draw the object with the same scale for the position. The heights don't have to be the same scale, but your horizontal distances all need to be the same scale, and the heights a different scale. And then draw the 3 rays that I'll describe in the next slide, and then determine if it's a real or virtual image and where it is and so on. So the descriptions of the rays are here. You need to know these descriptions. The parallel ray goes from the tip of the object to the lens or mirror, parallel to the principal axis, and then it reflects or refracts through the primary focal point. The focal ray is the reverse of the parallel ray. So it goes through the secondary focal point so that it comes out parallel. And then the vertex ray goes from the tip of the object to the vertex, and then if it's a lens, it just keeps going straight. If it's a mirror, it reflects back symmetrically. So here I will do an example. So I've already drawn on here, to save me some time, the principal axis. And the lens or mirror should have the principal axis at right angles to it, and it's going through the center. So in this case, I'm going to just choose to have a lens of f equals 5 centimeters and distance object will equal 10 centimeters. Okay, so this, you'll have something like this. I'll just give you numbers. And so the first thing is, what do I do with the lens? Well, it is kind of nice to just draw something like this to tell me, yes, I know that's a converging lens because it has a positive focal length. And I have my primary focal point and my secondary focal point. Now I need to add my object. So my object, I'm going to draw it as an arrow. And if this is the focal length of 5 centimeters, then it's going to be out here at 10 centimeters. And I'm doing this without benefit of a ruler. So that's, I think that's too close. It's not quite vertical, but we'll go with it. I think that's about right. So now I draw my rays. So let's color code it. Parallel ray is the red one. So I'm already on red. By the way, for the object, we usually put an arrow at the top. Okay, I can't stand the tilt on that. I'm going to try it once more. Or not. Can't erase it. No idea why it won't erase, but it won't. So we put an arrow there at the top, just to indicate that's the top. So my parallel ray goes from the object parallel to the principal axis. And then it refracts through the focal point because that's what parallel rays do. Next, we have the focal ray, which I think was green. Yes, the focal ray. The focal ray goes through the secondary focal point until it hits. And notice I'm going to that center line. I'm not worried about the blue lines I drew. And then that's going to come out parallel to the principal axis. And then finally, we have the vertex ray, the blue one. I didn't have a pre-made blue. Well, I'm actually going to make a blue one here just because line. I want to make draw a line, color blue. I don't have the patience. And let's make the width 2 instead of 1 point. So 2, 3, and 2, 3 points. Come on, there we go, 2. All right. So the vertex. And there you can see, wow, that came out pretty much perfect. All of my rays met at one location. It's kind of an amazing thing for me. And so here's my image. There's the tip of the image, and then it goes from there to the principal axis. Should be perpendicular to the principal axis there. And since that's the tip, I put that on here. And so in this case, I have an inverted image because it's upside down. It's real because the rays actually met there. They weren't projections. They were the actual rays that met. And then I would use a ruler to actually measure the height and get the magnification. Remember, magnification is equal to height of image over height of object equals minus distance image over distance object. The height image is negative because it's pointing down. Height object was positive. The distance image, which is this distance right here, is positive because they actually meet, or because it's on the side that the light went to. The distance object, this distance here, is positive because, well, the rays were actually there at the object, so our object distances are always positive, and it's on the side of the object. So you need to be able to do one of these, and this is one of the examples. Another one could have been with the object closer than the focal point. If the object was closer than the focal point, this red ray would be the same, but the blue ray would have gone down like this, and you see the red and the blue never meet, and so you have to extrapolate back to find where they meet. And of course, the green ray would have gone, well, like I drew. I'm not sure. Yeah, what did I draw that? The focal ray. This here, what I drew in blue was the vertex ray, and so the focal ray is the one that remains, which is the one that's supposed to be in blue. I drew the vertex ray. Oh no, it's green. Yes, green is the focal ray. In this case, the focal point is behind it, so it would go like this, and then come out parallel. And so then we extrapolate this backward, and then I would have my image. In this case, would have been there. A little better. That would have been my image. So this one is upright, has a positive image distance or object distance, has a positive height, but a negative image distance, and it's enlarged rather than made smaller. This one here was smaller. So make sure that you can do those. And remember, it could be a lens or a mirror. It could be a converging type or a diverging type. If it's diverging type, then the F prime is on the other side and the F is on the same side as the object. So it's because you have a negative focal length if it's a diverging type. I didn't talk about this yet, and this is kind of important. You need to be able to do this either graphically or by calculation. By calculation, whether it's a lens or a mirror, you have your relation 1 over F equals 1 over distance image plus 1 over distance object. And so using that equation, you can, having two of them, either, well, two of the three, focal length, distance image, and distance object, you can then calculate what the remaining one is. And that was derived through geometry. So this works for both lenses and mirrors. For a mirror, focal length is equal to the radius of curvature over 2, where converging is positive and a diverging is negative. For a lens, we actually have a lens maker's equation, which we didn't go over, so you won't be using geometry to calculate the focal length of a lens, other than to know that if it is thicker at the center, then it's converging. If it's thinner at the center, then it's diverging. All right, chapter 26. This, we dealt mostly with the eye. In fact, I forgot to put anything. Oh, no, I did. I thought I forgot the optical instruments. With the eye, we talked about only four simple vision problems that we can fix with physics. Myopia, otherwise known as nearsighted, you can see near things, but you can't see far things. Hyperopia, otherwise known as farsighted, you can see far things, but not near things. Presbyopia, old person vision, that's when that crystalline lens hardens, so you cannot adjust your focus, so it stops you from adjusting your focus to see close things. Now you could have hyperopia and presbyopia. Now hyperopia, we call that far sight, you can see far things, but the presbyopia is going to make it so you can't adjust as much to see near things, so you see worse in terms of near things. You could also have myopia and presbyopia. Nearsighted, you can see near things, but presbyopia, you don't have as much accommodation, and the end result is presbyopia and myopia. You can't see near and you can't see far. That's pretty bad, and so that's why we have bifocals. Now, know how to correct these. So for myopia, a myopic person, either their eyeball is too long or the cornea, or no, yeah, that's right. Or the cornea is too, okay, I'm actually saying this wrong. I must think. If you have myopia, your eyeball like this, the cornea does the primary focusing, and you have things that are far away, so parallel rays, come to a focus too early. If something is closer, then it'll come to focus on the back and you have no problem. And so that's what causes myopia. Yes, the eyeball is either too long or the cornea is too curved. That's where I was messing up in my description. So the eyeball too long, or LONG, come on, or cornea too curved. So you correct that with a diverging lens, or today you could have a laser surgery to flatten that cornea. Hyperopia is just the opposite. The eyeball is too short or the cornea is too flat. And so you correct that with a converging lens or a laser surgery that actually makes the cornea more curved. Presbyopia, that's the one that's not the cornea problem. That's when the lens gets hard. So it doesn't deform as easily. You can't adjust your focus because you adjust your focus, what we call accommodation, by deforming that crystalline lens that comes just behind the iris. And so in that case, you don't have as easy a fix, but we use bifocals so you can focus on something near and far. Astigmatism is a symmetry problem. You have an asymmetry of the cornea. And so that's fixed with an asymmetric lens. Now you should be able to calculate how to correct for vision. So if you have a person that's myopic, you'll generally be given their actual far point, and then you need to choose a lens that will take an object at the far point, the normal far point of infinity, and create an image at the actual far point. For hyperopia, and don't worry about the presbyopia here, just for hyperopia, we take the normal near point is 25 centimeters, and you take an object at that normal near point, and you need it to make a virtual image at the actual near point. So it's really simple lens, as simple as it gets, lens problems, but you have to know how you do the correction for myopia or hyperopia. Finally, for chapter 6, optical instruments. So you should know the purpose of a telescope. That's to magnify very distant things, which are generally also very large. Microscope is to magnify very small things that are very close. You should be able to calculate the magnification of a simple magnifier. That is, I have my eyeball and I put a lens in front of my eyeball, and it allows me to bring something closer. So I can bring the object closer to the focal point is what we usually do, so you can have a relaxed eyeball. And that allows us to make a bigger image. Magnification angular is equal to the aided angle that it makes divided by the unaided, what we would make if it was at our near point. And so what we get for this is, if it was aided, then the object is one focal length away from the lens. So that's going to be, the angle is the height of my object divided by the focal length. If it was unaided, it would be at the near point. And so that's equal to near point over f. That's magnification for a simple magnifier. And notice it's angular magnification. Now for a microscope, you have the objective lens, the lens that's closest to the object. You put the object close to that, which makes a magnified transverse magnification image that then is the object for the eyepiece. So the eyepiece magnification is still going to be this, and you have the transverse magnification of the eyepiece. For a telescope, you have something very far. You put your objective lens there, and it creates an image, and the magnification then for the telescope turns out to be, if here's your objective, here's its focal point. If you have something infinitely far away, Then this is the theta unaided, and this is the height of the image. And then you have, here is the eyepiece, and this angle here is the theta aided. And so using trigonometry, theta aided is equal to height of the image. Notice that was height of object over focal length of the eyepiece. And the theta unaided was equal to the height of the image over focal length of the objective. One thing to keep in mind is one angle is measured down on the right side, one's measured down on the left side. So one of these has to be negative, so I'm just going to put it there. And so then the magnification is minus focal length of the objective over focal length of the eyepiece after you cancel the height of images. So make sure you understand how these work. For the telescope, there's the focal length of the objective. Here's the focal length of the eyepiece. So the length of the telescope is the sum of the focal length of the objective and the focal length of the eyepiece. For the microscope, we had a more complicated equation. You'll be given the equation that magnification for the microscope is equal to, what is it, n times, I don't remember what it goes up here. There's something here, and I don't even remember, but you'll be given that equation. And so you need to understand what they do, what their purpose is, and be able to calculate magnifications and things like that. Finally, chapter 27, wave optics. These are things that light can only do if it is a wave, which at this point is all we know. But in the future, we're going to learn about a particle nature of light. And so it's important to have those two and understand reasoning why we say light is a wave. So the first and foremost thing we talked about that says light has to be a wave, you've got Thomas Young, a Nobel Prize, is a diffraction gradient. If you have light that goes through two slits and you look on the screen, it will make not just two bright spots, but a number of bright spots with the biggest one in the center. And that's not possible if I was just shooting BBs through those holes. If I was shooting BBs through the holes, I would have just seen 1, 2 with a dark spot in the center, right? So it can't be particles, can't be like BBs. It's got to be a wave where we have waves that go through here. And at some points, the difference in the paths makes them so they're pi radians out of phase, and thus destructive interference. And other places, it's the same distance or an integer multiple of the wavelength different. So it's constructive, and we build up a positive constructive interference. So you can't have constructive and destructive interference unless you have waves. So light has to be a wave. And we learned equations for double slit, d sine theta sub m equals m lambda for constructive, two slit, or n slit if it has more, and d sine theta m equals m plus 1/2 lambda for destructive, two slit or more. But what about the single slit? Well, the single slit was a lot more confusing, but the single slit, we just had a destructive equation, and it turns out that for a single slit, the destructive equation looks very similar to that. Capital D being the width of the slit, sine theta m equals m lambda for destructive for one slit. And with the one slit, capital D is the slit width. For two or more, lowercase d is the slit separation. In both cases, m was any integer. And it's just numbering which fringe it is. So the center one here was m equals 0. M equals 0 for that one, and then it was -1 plus 1. Let's make that side plus. So that can only occur if light is a wave. Another thing we looked at was thin film interference. In the homework session that we just finished, homework 27, we reviewed what we talked about in the lecture about the thin film interference, and you won't have an equation for this because it depends on what the indices are, what you're going to get. So if I have air, water, air, that is, it's a bubble that I'm blowing, I have N2 is 1.33, N1 equals 1.00, N3 equals 1.00. If I want to look at reflection of light off of that surface, the light comes in and I have some light that goes like that, some that goes like this, and I need to take the phase difference between those two. So I have phase one. If I reflect off of water, water has a higher index of refraction, and so I have V1 is equal to pi radians, because if you reflect off of something with a slower speed or with a higher index refraction, same thing, then you're going to have a phase inversion, a shift of pi radians, or 1/2 wavelength if you were talking about distances. For the second one here, when it reflects, it's reflecting off of air. Air has a smaller index refraction. It doesn't have that phase inversion. But you have the additional path length, so you have plus 2 thickness times 2 pi radians divided by the wavelength in the water. But the wavelength in the water is equal to the wavelength in air divided by the index refraction of the water. And so that would be, if you put it all together, 4 pi thickness N2 divided by the wavelength in air. And so that's the difference in phase. And then you take, or that's the phase for two. We had the phase for one, in this case was pi. Take the difference in those two. And if it's constructive, if you're looking for constructive interference, then you're going to say, well, that difference is equal to m lambda for constructive, right? Same as we had for constructive interference here. And if you are looking for destructive interference, then it's going to be m plus 1/2. Actually, I said lambda. I did this in phase, so constructive difference in phase is equal to m times 2 pi. For destructive, the difference in phase is equal to m plus 1/2 times 2 pi. And if we'd done path length differences, I would have had delta L is equal to m lambda. Delta L is equal to m plus 1/2 lambda for the difference in path lengths. So we did path lengths when we did the diffraction grating or double slits, and we did phases when we did the thin films. So there's lots of different variations, and you should be able to explain how you get an equation for constructive or destructive interference on transmission or on reflection. Finally, there was polarization. Polarization, it can only work with a transverse wave, not just a wave. It has to be a transverse wave. With electromagnetic waves, we have electric field or magnetic field as the amplitude or as the displacement. And so by tradition, we just talk about the electric field. And so a polarized light wave has electric field that is only oscillating in one direction. Now remember, the electric field has to be perpendicular to the velocity, but it's only oscillating in one direction that's perpendicular to velocity. Now, if you have unpolarized light, you have the electric fields oscillating in all of the directions that are perpendicular to the velocity. And if you have unpolarized light and it goes through a polarizer, it's going to then have the light that comes through is only oscillating in the transmission direction of the polarizer, and the intensity is cut by half. Otherwise, if I have polarized light and it goes through a polarizer with an angle theta between the incident polarization and the angle of the polarizer, then the transmitted intensity is equal to the incident intensity times cosine squared of the angle. So you have two rules. Polarized light follows that unpolarized light, the transmission is just 1/2 of the incident light. Okay, that should be a review for the exam. Those are the topics that are going to be covered, and I'll send out a sign-up sheet for you to sign up for 1-hour periods. It's going to be oral exam. Because it's only a 1-hour period, it's going to be a shorter exam than what you're used to taking. All right, look forward to getting this out of the way.